All right, I'm going to pick up right where I left off with number 15 to get the standard deviation. There's a couple different ways you could do this, so do what makes the most sense to you. But after you found the mean, one option would be to just say, okay, remember standard deviation is a distance, right? So we could say like 102, the high limit up here, minus that mean, and get that difference. Let me see, 102 minus 96.5. And then, here we go. And so I'm getting 5.5. And notice that that's a span of 2 standard deviations. So you could divide that in half, and I get a sigma of 2.75. That would work just as well on the lower end as well. If you did 96.5 minus the 91, you would get the exact same result. So you could do it that way. The other option would be to do the entire thing, 102 minus 91, and then divide it by 4, because that's the entire thing. There's 2 sigmas, remember, on each side. The entire would be a span of 4 sigmas. However you want to do it is fine. I don't care. Just make sure that you draw a picture for this and kind of reason through it. Sigma, remember, is the distance, standard deviation, and then mu, of course, is the mean. Remember, that's going to go right in the middle. Let's go down to chapter 7. That's the last part of the test. So a couple things to remember. Make sure you remember the difference between a parameter and a statistic. So a parameter is any measurement on a population, any measurement. So a mean, a standard deviation, a proportion, any of those are really the ones we focused on. If it measures the population, then it is considered a parameter. If it measures the sample, then it is considered a statistic. So make sure you remember the difference. Also make sure you remember the symbols for each of these. So for statistics, if it's a sample mean, we use X bar. If it's the sample standard deviation, we use lowercase s, and if it's the sample proportion, we use p hat. For the population, if it's a mean for the population, remember we use mu, and then if it's the standard deviation for the population, we use sigma. That's what goes with that normal distribution, because theoretically the normal distribution measures a population. That's the idea. And then if it's a population proportion, we use p. This may be something to put on your index card along with the definitions of parameter and statistics. So remember that parameters always go with populations, statistics always go with samples. Let's look at number 19. 19 is a representation of the central limit theorem, and so there may be a question like this on the test. Let's take a look. Samuel Morse suggested in the 19th century that the letter T makes up 9% of the English language. Assuming that this is still correct, we take a random sample of 1,000 letters from a large book and we count the number of T's. A says, what does 9% represent? Well, ask yourself, that's a percentage, but does it measure a population or a sample? Well, the 9% of the entire English language would be the measurement on the population. So this would be P, and that would be your population proportion. In our sample of 1,000 letters, so n is equal to 1,000. Remember, n is sample size. That's another symbol we might need to know. N is 1,000. What would we expect for our sample percentage of T's? So we expect, our expected value for p hat would be 9% of 1,000. So we expect to get 9%. If we take a random sample, we expect our sample percentage to be the same as the population. So I'm going to do 9% of 1,000, and that gives me 90. In other words, just 0.09 times 1,000 gives me 90. So I should expect to get about 90 T's in my sample. Standard error, make sure you know the formula for standard error for a population proportion. That would be P times 1 minus P divided by N. If you know P, always use P. That's very important. This would be a good formula to put on your index card. So I'm going to use 0.09 for P. Make sure you use decimal, not percentage. 1 minus 0.09 divided by N, which was 1,000. please put that in your calculator and make sure you know how to push those buttons in your calculator correctly. Make sure you remember to take the square root. That's something students often forget, but I'm getting about 0.009, it looks like, as my standard error. So it says we would expect to get blank percent t's. We would expect to get 9% t's, give or take our standard error. So our standard error, I know there's a lot of nines here. Don't get confused with this example. Try to keep everything straight. Our standard error as a decimal was 0.009. So as a percentage, if we move that 2 spaces to the right, that's 0.9%. So that's coming directly from my standard error. Okay, sorry, I don't want to confuse you with this equal. Let me get rid of all that. So we expect to get 9% t's, give or take about 0.9%, which is the standard error. So this is the p, and this is the standard error, both as a percentage. Now F says, would it be unlikely to get a sample with 120 t's, and how do you know? Anything that is more than 2 standard errors, just like when we said 2 standard deviations in the previous unit, 2 standard errors is considered unlikely. So what I would probably do for a question like this, you could calculate the z-score, but I think a quicker way to do it would be just to go ahead and look at, okay, if I have 9% is what I expect to get, 9%, my standard error is 0.9, 120, remember we said 90 was what we were expecting. Now let's do it this way, actually. Let's do it this way. Let's use numbers instead. Let's say we expected to get 90 t's. I'm asking about 120. So 0.9% is my standard error. How many t's is that? So my standard error would be, let's see, 0.009 times 1,000. So if we do 0.009 times 1,000, I'm getting 9 again. So my standard error is 9. So 1 standard error above would be 99. 2 standard error above would put me at 108. So if I'm at 120, is that outside of 2 standard errors? Yes, 120 would definitely be considered unusual because it's past 2 standard errors. Last question, how could we improve the precision? Precision is the standard error, basically. That means you want to reduce the standard error. And the way we do that is we increase the sample size. So I'm going to just abbreviate and say increase n. So to improve precision, we increase the sample size. That's important to remember. Let's take a look at number 21. I think that's the last one I'm going to worry about here. But also I was going to mention skip 23 and 24. There's nothing from chapter 8 on the test, so don't worry about those. But take a look at 21. It says, a June 2012 Rasmussen poll showed that 65% of randomly selected U.S. adults were opposed to banning sugary soft drinks with a margin of error of 3%. Now, one thing I want to mention on the test, if we ask you to do a 95% confidence interval from hand, we are going to ask it this way. You do not need to know how to do it using the standard error with those z-star values I got into. Those were a little confusing and a little hard to do without StatCrunch. So to do a confidence interval by hand, what you need to remember is that it's going to be p hat plus minus the margin of error, and that is all we have to do. So if the margin of error is 3%, that is it. Don't double it, don't do anything else with it, just use that. So you're going to do 65% plus minus 3%. So my lower bound would be 62%, my upper bound would be 68%. And so my interpretation, we would say we are 95% confident that the proportion of all U.S. adults, and I'm sorry, I'm really short on room here, all who would favor, or who would oppose the ban is between 62 and 65, or I'm sorry, 68%. Remember, we pull a sample, and then from there we make an inference to the larger population. So we're making a statement about the population proportion. We think the percentage of all U.S. adults, that's the population. Please do not mention the sample. When you write your confidence interval, you are only discussing your population. We are 95% confident that the proportion of all U.S. adults who would oppose banning supersize sugary drinks is between 62 and 68%. Now, it's based on this sample that we took, but it's an inference about the population. That's the idea. C says if the sample size were larger but the sample proportion stayed the same, would the interval be wider or narrower? So think about a larger sample size would reduce the standard error. Just like we said back here, and we talked about precision just a moment ago. Improving precision means we want to reduce standard error. We do that by increasing the sample size. So this is kind of the opposite. If we increase the sample size, we lower the standard error. So if we lower the standard error, that gives us a narrower confidence interval because that means we're including fewer standard errors in our interval. D says if the level were increased to 99% instead of 95%, but nothing else would change, would the new interval be wider or narrower? So if we have a higher level of confidence, it's the opposite of what we just talked about. So a higher level of confidence means that we're going to have a wider interval. So a 99% interval means we're using more standard errors, so it would be wider than a 95% interval. All right. I think that's pretty much what you need to know for confidence intervals. Make sure you look over central limit theorem. Make sure you know the symbols and definitions from the beginning, chapter 7, 7.1. Those are definitely on the test. But as always, please email me. Let me know if you have questions. I'm happy to go over this more specifically. Just let me know.